Welcome back to another lecture video. We're going to continue on with the chapter of eigenbases and eigenvectors and eigenvalues. We are almost done with this chapter, and additionally, we are almost done with the topic of linear algebra as a whole. So that is crazy. So now that I mentioned that, let's actually get into the lecture itself. And so this lecture, we are going to talk about diagonalization. But before we get into diagonalization, I do want to have a quick little review with eigenvalues and eigenvectors. And so last lecture, I discussed the process of finding eigenvalues, and I also did a couple of examples that have been posted not too long ago as well. And so to find the eigenvalues, well, what we have to do is to find the roots of a characteristic equation, in which case the characteristic equation is the determinant of lambda times the identity matrix minus a, and you set that equal to 0. Another way that you can write this equation is, which is like my favorite way of writing it, is the determinant of a minus lambda times the identity matrix, and set that equal to 0. And so when you find the roots, those roots will actually be your eigenvalues for that given matrix. And so one way we can check that these eigenvalues are actually from the matrix is if their sum of all the sum of all eigenvalues that you found is equal to the trace of the matrix, then you pretty much know that this is your eigenvalues that you found. Another way you can check it, which can be a little bit longer depending on what matrix you're working with, is taking the product of the eigenvalues. What's unique about that is when you take the product of the eigenvalues, it will essentially be equal to the determinant of the matrix. So if you know that the product of the eigenvalues is equal to the determinant, then you have your eigenvalues. Like I mentioned, it can sometimes not be so quickly checked if you're working with like a 4x4 or 5x5 matrix, but it is useful when you're working like a 2x2 and in some cases a 3x3 matrix. Another thing I want to talk about is multiplicity, and I did talk about it just a little bit in last lecture, but I only discussed about one type of multiplicity. And so there's two types of multiplicity. The one that we discussed, which is the algebraic multiplicity, and that is the number of times the eigenvalue appears as a root of the characteristic polynomial. The other type of multiplicity is the geometric multiplicity. And the geometric multiplicity tells us, or is the dimension of the nullity of the matrix A minus lambda I. And so one thing about these two is that the algebraic multiplicity will always be greater than or equal to the geometric multiplicity. And depending on which case it is, it can actually tell us if we're going to be playing, or if the matrix is going to be playing nice, or we're going to have to get a little bit messy with it. Ideally, we want the algebraic multiplicity to equal to, we want the algebraic multiplicity to be equal to the geometric multiplicity, and which you'll soon find out in this lecture. But if that is not the case, which means the algebraic is greater than the geometric, then things can get messy, and I will discuss later in the future on how we can deal with those. So now that we got this quick little review with eigenvectors and eigenvalues, we can now talk about diagonalization. Before I give a formal definition or tell you what diagonalization is, I want to first discuss about matrices, similar matrices, my bad. I want to discuss about similar matrices. So if we're given two matrices, A and B, then if both matrices are similar to each other, then that means there exists an invertible matrix that we're going to call P, such that matrix B will equal to the inverse of P times A times P. Now that we have that definition of what a similar matrix is, some mathematicians kind of proposed a question with this definition. So if we have a square matrix A, can we find an invertible matrix that we're going to call S, such that when you take the product of the inverse of S, multiply it with A, multiply it by the matrix S, would that be equal to some square matrix that we're going to call D, such that D is a diagonal matrix? And what they ended up finding is, yes, you can actually find that. And so any matrix that is similar to a diagonal matrix is what is known as diagonalizable. And obviously this is with the condition that we are working with square matrices. And so diagonalization, and what diagonalization is pretty much the process of taking a n by n matrix or a square matrix and converting it into a diagonal matrix with an invertible matrix that we're going to call S. And so an n by n matrix is diagonalizable if and only if it has n linearly independent eigenvectors. And this is very crucial because if we have n linearly independent eigenvectors, then that means the algebraic multiplicity is equal to the geometric multiplicity. And that's what I meant by the first case on like how things work out really nicely. And so how will we find this diagonal matrix D? So we can break this down into a series of steps for diagonalizing a square matrix. I will say any, but that's not necessarily the case. So before we get started, let's actually define our matrix. So we're gonna let we're gonna let A be any n by n matrix. And so the first step, the first thing that you must always do when it comes to diagonalizing matrices and just eigenvectors and eigen values is to find the eigenvalues with the corresponding eigenvectors. So that means taking the characteristic equation of the matrix, setting it equal to 0, and finding the roots. And so once when you find the eigenvalues, you go ahead and find the eigenvectors. And we have to check that there are n linearly independent eigenvectors. If there's not an n number of linearly independent eigenvectors, then that means the matrix is not diagonalizable, and that matrix is what we call defective. And so let's just say that we have n linearly independent eigenvectors. Then we're going to go ahead and move on to the next step. So the next step is to create a new n by n matrix that we're going to call S, and that consists of the eigenvectors. And so the eigenvectors, you're going to write them down by columns. So the first column will have one eigenvector, the second column will have the other eigenvector, and so on and so forth. And so when you create that matrix S, you're pretty much almost done with diagonalizing the matrix. And so all we have to do is find the diagonal matrix, which will be the inverse of S multiplied by the matrix A multiplied by S. And so what this will give us, it will give us a diagonal matrix in which the eigenvalues will be along the main diagonal. And that matrix, again, will be our diagonalized matrix. But other than that, that's pretty much it for this lecture. This lecture will consist of so many examples because there's so many things that you can do with this. And yeah, that's pretty much it. I'll see you guys in the Blackboard.